Thanks for stopping by the channel today. My name's Jason. I'm KC5HWB. This is the extra class. This is the final class in the 3 classes of amateur radio licensing that exist in the United States today. Some of my most popular videos on this channel have been the technician class and the general class, which is class 1 and class 2, or level 1 and level 2, if you will. This is level 3. This is the final level. This is the top license you can get. And I want to thank the North Richland Hills Amateur Radio Club for allowing me to record this Zoom class they did at the end of 2020, beginning of 2021. It was about 8 6 to 7 hour sessions, so you're in for a wild ride today. Go through them as many times as you want to. Fast forward, stop, pause, rewind, whatever you want to do. Play them over and over again. This is good information for those of you who are currently a general and wanting to upgrade to amateur extra. Thank you to the North Richland Hills Amateur Radio Club. Their website will be linked in the description of the video below. And I hope you enjoy the video series.
Yeah, I think I've got the whole page up there. What we're doing is going over this chapter that starts on page 123 of the Gordon West book, Receivers with Great Filters. And then we'll go over the questions after we go over this chart. I made this handout in relation and in response to a question last week about sharing the handouts. I made this all myself, and it can be freely shared. So we already sent it out. You've got it, and looks like it's in public domain. That's fine. I'm not going to make any money off of it. Okay, so everybody's got that. Basically, what's going on here is the design of a superhet radio receiver. I call it a radio, but it's a superhet receiver. And across the top is the block diagram of it. And then there's various parts and various details about superhet receivers and receivers in general, and then we'll get into the software-defined radio a bit, all following the questions in the question pool for the extra class. And we'll go through the concepts, through how all the concepts relate together in the order of a receiver, and then that will, I'm hoping, help everybody remember what's going on in receivers so you can better understand what the questions are talking about. That's my goal anyway. Okay, so we'll start in the top left up here with this upside down coat hanger wire. And everybody knows that, well, or that is the schematic symbol for an antenna. That's one of them. The other one looks like a crow's foot, and there's probably some others that are valid just as well. But that's where we start. The first thing we encounter is a filter. So let's talk about filters first. So I'll refer to the lower left-hand corner, lower left-hand part of the screen right here, and just say that filters are defined by their center frequency and bandwidth. The bandwidth is usually taken toward the top of the pass band. The pass band is maximum amplitude through the filter. The stop band, or it can be also referred to as the shape factor, is measured quite a ways down on the skirts of the filter. The slope sides are called the skirts. We have the pass band. We have the stop band. The stop band is where the attenuation is the greatest. Now, this is the way I've always drawn filters. Other people draw them upside down, what I refer to as upside down, where the minimum loss is at the bottom end, But here, the minimum loss is the passband. So I like to draw that so I can see that the passband is where signals are coming through. The attenuation on the slopes is where signals are attenuated. And off in the stop band, there should not be any signals coming through. So without this stuff on the left-hand side where it says notches, this would be the filter shape of a Chebyshev filter. You need to remember that name. That was a Russian research mathematician, and he came up with the methods to design these filters. Chebyshev filters have some ripple in the passband, as I've shown here. Some filters are smooth across the passband, but Chebyshev will have ripple. Another type of filter is elliptical filter. It's all, the name comes from the mathematical method that's used to define the filter. We're not going to go into that. That's too deep for, and not covered in the scope of the extra class license. So we're not going to go into the mathematics of it. But one of the results of using the elliptical method to define a filter is you get notches out here in the passband, in the stop band. So in the stop band, the filter response actually dips down to very sharp notches and very deep attenuation. But then that means that there's some little humps, flyback of low-level signals of some attenuation, but there are notches in the passband, and between those notches that would extend down below the horizontal baseline here are places where where off frequency high power signals would come through. Now there's some problems with those, and we'll talk about that in a second, that causes. But every filter in a radio is going to have these general characteristics. Some filters are narrower than others. Some filters are wide. And so that's how we say filters are defined by the center frequency where they're tuned, and the bandwidth, how wide the filter is, how wide of frequency range will pass through the filter. That's the passband. We can talk about interference sources. So if the first thing that signals see when they come into your receiver is a front end filter, sometimes it's called a preselector. It removes strong out of band signals. So if the center frequency here is tuned to like 7,200 kilohertz, the middle of the 40 meter band, well, that'd be the upper end, but 71 kilohertz would be about the middle of the 40 meter band. Then this could extend a megahertz or two, or a few megahertz wide. Hopefully something that keeps out a lot of signal, a lot of energy at different frequencies that comes down your antenna. Like anything, like it would keep out 80 meters at 3.5 to 4 megahertz. It would keep out 20 meter signals. It would keep out 15 meter signals at 14 and 21 megahertz, and everything else. A good thing that a preselector should have would be to keep out the AM broadcast band, because those are horribly big signals, and your antenna is probably picking those up very well. So that would be the front end RF filter or a preselector to get rid of out of band signals. Let's see. Well, let's not talk. That's toward the end. We'll talk about interference sources. Okay. The next thing that signals coming into your receiver will encounter a couple of different things, and these can be arranged in different orders. They don't have to be this order. Sometimes the preamp is the first thing the antenna gets to, and there's problems with that. There's a thing called desense. Desense is a word that describes what happens to an amplifier if you have strong signals, strong RF signals coming into it that makes it clip, that limits the gain. Clipping is bad because that causes other distortion. Limiting the gain is more a desense function, in that the amplifier, if it gets to clipping, it's not going to amplify the real small, low-level signals at all. And receivers, I didn't even talk about AGC because that's not on the test, but receivers can have gain stages where the gain is reduced by the AGC or by the RF gain. I didn't even show the RF gain control on here, but most receivers will have that and AGC, but that's not part of the test. But the gain, if the gain of an amplifier is reduced by strong signals, that's called desense. So it'd be better, see, to have the preamp after you have a front end filter to limit these strong out of band signals, so that you limit the desense going on. Because when you get desense, you have a strong out of band signal you may not even be hearing, but all of a sudden what you're listening to is just going to go away if the gain is reduced to a very low level, or its amplitude is going to be reduced. Now, something you can do, a stage you put in a receiver that reduces this effect, is an attenuator. Attenuator is like a volume control. In modern receivers, it's switched. One of my receivers has a couple of different stages of attenuation and a couple of different gains for the preamp. The attenuator reduces the signal level going to the rest of your receiver. That's useful if you've got a neighbor that lives 4 houses from you and he likes to run kilowatt and you're trying to listen to some small signals. Well, I can put in the attenuator and attenuate his signal enough that it doesn't cause desense in my preamp. And that's a good thing, because then I can continue to operate while my neighbor up the hill is transmitting on his kilowatt. He doesn't have much on me, maybe 20 feet, but still, when he puts out his kilowatt signals, it causes desense in my receiver. This is desense over here. After the preamp and attenuator, there's another type of filter that's inserted in receivers sometimes called a roofing filter. And this attenuates strong signals near the receive frequency. Now it's not as wide as the Preselector. It can be a few hundred kilohertz wide, but still, if it's at the RF frequency, it's going to have to be tuned in the receiver. And modern receivers, especially the ones with DSPs, do all this automatically for you. The roofing filter is another type of filter. It's not as wide as the Preselector. I'll put down here a few hundred kilohertz. Something wide enough to where you could tune over a good part of a band. This receiver diagram can be at any RF frequency. It doesn't have to be HF, VHF, UHF, microwave receivers, anything can all be described by this block diagram. So after the roofing filter, we go to this stage called the mixer. Now the mixer is the magic part of the superhet radio that was invented, it's over 100 years ago now, when it was invented at the very beginning of radio technology. It takes another stage for a mixer to work called a VFO, or a local oscillator. And we'll get into oscillators later on in another chapter, next week or the week after. I forget when it occurs. It's all about oscillators and synthesizers. Here I've sketched out a LC oscillator with a gain. You take this gain, provide some feedback, and we'll get into those type of oscillators and how they operate and their circuit diagrams. But I didn't draw all that on here. Just to show you, there's an oscillator and then a filter after that to remove harmonics. And this is a filter prevalent, and it's almost like a preselector filter that's prevalent in VHF and UHF radios. And you have to have those to keep harmonics out, because if you feed harmonics up here to your mixer, that's other frequencies that the RF can mix with and cause signals to go through your receiver that you don't intend to have. So we've got this mixer, which is the heart and soul of a super heterodyne radio. The heterodyne refers to the mixing process, where you take the VFO, the local oscillator, with your incoming RF signal, and you mix it to where you get output signals, and what comes out are the two input signals plus the sum and the difference. Now, you can use the sum or difference because you can have the local oscillator be at a higher frequency than your RF that you're receiving, or it can be lower frequency than the RF you're receiving. But you get both. You get the sum and the difference. And so one of these, the sum or the difference, falls on the fixed filtering frequency of your IF. IF is an intermediate frequency stage in the receiver. Now the bandwidth of an IF filter is way narrow. It's the bandwidth, in fact, is matched to the modulation that you're expecting to receive. There's several reasons you do that. One is because if you get your whole modulation you're receiving matched to the bandwidth of the IF filter, you have the greatest signal to noise ratio. And that's what a receiver is all about, is to maximize the signal to noise ratio. So right here, maximum signal to noise is the ratio of the signal strength to the noise strength. And noise in a receiver is an inherent quality. Noise is inherent, is inherent in any electronic device. There's noise. So you've got noise coming in your antenna that comes through the same frequency as what signal you're trying to receive. You've got noise inherent in any of these electronic components. Even resistors have noise. Now, capacitors shouldn't have noise, but maybe some of them do. And there are capacitors that have other problems, but resistors have noise. Electronic amplifiers, the amplifiers have noise, the mixer has noise. And so you want your signal to match your IF bandwidth and fill up the IF filter with the modulation bandwidth for the intermediate frequency. Now, one type of filter you can use for the IF is called a crystal lattice filter. It's made up of crystals, the same type crystals that we can use to form oscillators. You put some of those crystals together in a particular arrangement, and it's called a lattice filter. And it's very good for making this narrow band, even down to several kilohertz, a few kilohertz wide. There's analog filters that can do this. One of my old receivers has a 455 kilohertz IF, and there were years ago, this is from a 1960s receiver, my first novice receiver. I've still got it just because it has a 455 kilohertz IF, and it has a second IF with further filtering at up in below 100 kilohertz range. So it's a dual conversion. You don't need to know all that. It's a 455 kilohertz, and it's L's and C's, inductors and capacitors that make up that filter. So there's other types of filters besides crystal filters. And what this intermediate frequency does is it removes adjacent channel modulation. Because if you work on the 2 meter band a lot, you know that every, what's the spacing? 600 kilohertz? No, that's the repeater offset. Every 25 kilohertz, or some areas it's at 50 kilohertz, the channels are spaced out at 50 kilohertz or 25 kilohertz. So if this filter, and the filter for FM radios is typically 12.5 kilohertz. So at 25 kilohertz away, which is almost that same IF filter bandwidth away, you've got another repeater output. So you want to hear the one you want to listen to sitting here where the IF is tuned. You don't want to hear the one that's adjacent. So that's called the adjacent channel attenuation. And the IF filter removes adjacent channels and other close-in noise, because any noise that comes through this roofing filter and gets to the mixer is going to be mixed down to the frequency range around the intermediate frequency. There's some a part you can use, another stage you can use in the IF called the noise blanker, but it makes signals look wider when you use it. And there's problems in spreading out signals, because when you take the desired modulation on the desired channel that you're really trying to receive and you spread it out, it just makes a whole wideband noise that comes through your IF, and it reduces or it increases the noise that's coming through your IF filter, and that's not a good thing. Another thing you have to watch out for with a mixer is called an image. Not only do you get the local oscillator mixing with the channel that you're receiving, and let's say you're looking for the difference over here to hit your IF filter at the right frequency, you also get the sum of the LO with the noise coming through roofing filters. So the image is a thing, is a signal, another signal that's mixed into your IF frequency, and it's figured from the receiver frequency viewpoint, it's plus or minus 2.5 times the intermediate frequency. This is F of your frequency of your intermediate frequency. Now you'll have to know this. There's a picture of it that will go through. Well, if you don't have a book, you can't see the picture. But what happens is either side of your local oscillator is signals that are mixed down to your intermediate frequency. So your local oscillator frequency mixes the signals above itself by the IF and below the frequency of the local oscillator. And both of those will mix into your IF. And the one that you don't want is called the image. Out of the mixer comes the two inputs, which are at RF, which the IF rejects very well. But the sum and the difference get in there and they go right through your IF filter. Let's say the sum of the local oscillator plus the RF frequency is the one you're wanting to put through your IF filter. On the difference frequency can be some phase noise. Local oscillators have phase noise that come through, and they're mixed in as part of the image response. Another part of image response can be off frequency, very high signal levels coming in your antenna, or sometimes it just sneaks into the receiver mechanics. Your receiver case is not shielded well, and you can get mixing in from that source. But that's too much information. That's not on the test, sorry. I'm sorry, I've been doing this for designing radios and studying radio designs for 50 years, and I can just carry on forever.
Wayne, can I make a couple of observations that might be helpful to some?
Go for it.
The brilliance of the super heterodyne receiver is that IF filter, because you can make an IF filter for one frequency that has exactly the shape you need. And by heterodyning or mixing the local oscillator frequency with the incoming signals, the signals are all processed at the intermediate frequency. For the old AM radios, 455 kilohertz was the standard. The crystal filter that I have in my Yaesu 857D.
Hey, John, your microphone.
Thanks for the reminder. I don't have it on my head. The crystal filter in my radio is an old Collins 455 kilohertz, 500 hertz wide CW filter. And, you can change those filters depending on the modulation, but that's the genius of the super het receiver. The problem, of course, is what Wayne's talking about, is that image. If you're receiving a broadcast signal at 1 megahertz and you've got a 455 kilohertz IF, the local oscillator is going to be at 1455 kilohertz, and the image is going to be at 455 or 910 kilohertz or 1910, which is in the ham band. So if you're trying to listen to 1,000 kilohertz, 1 megahertz broadcast station, and your next door neighbor is sending Morse code on 1910, that image frequency may come through even through all of the filters, and you hear the CW in addition to the broadcast. Does that make sense? That's the genius of it.
Yes.
I'm done.
Okay, good. Thanks, John. That goes over and helps explain some of the problems with the mixer. I've got a long list of them right here that we need to talk about. Now the mixer comes with some extraneous effects besides the image. You have a dynamic range problem. The mixer is an active electronic component. JFETs, MOSFETs are typically used right there. Well, tubes first, and then JFETs and MOSFETs. But I designed with JFETs and MOSFETs in my receiver design experience. So dynamic range means you get a real strong signal coming in here. It could be off frequency and not one that's not going to hit your IF filter. But when you get that strong off channel signal coming into your receiver, it's going to reduce the gain and cause dynamic range problems. And we'll talk a bit more about dynamic range here in just a minute. Let's see, we talked about, the image, but there's another spurious signal that comes through mixers very well. That's called intermod. It takes 2 times one frequency, subtracts another, and that causes signals to come out into your IF filter that will pass right through the IF filter, just as though they were the desired channel frequency that you're trying to listen to. That method is called intermod, and we'll go over an example of that here in a few minutes. Let's see, we talked about the image. Now, one way to reduce the effect of having an image in the mixer, all mixers will have image responses, but one way to reduce that is to use high IF frequencies. That is, don't pick an IF that's close to the RF frequency you're trying to listen to, but use one that's real high. And something that happened, I don't know, 20 or 30 years ago is that HF radios started using like 60 and 70 megahertz for the first IF. And then they would use another mixer and down convert from that. But that would get rid of the image in that first mixer. Let's see, we talked about the phase noise coming from the local oscillator, also mixes into your IF filter. We have third order intermod. That's where you have 2 plus 40 dBm signals, which is more than a watt, that mix together in your mixer, because they're strong enough to activate the mixer and use those themselves as a local oscillator, and they make a normal signal level product that goes into your IF filter. Now mixers, because mixers are nonlinear circuits, they work kind of like square waves, and so the odd order products, in particular the third order product, are within the band. And that's why we call this the third order intermod. It's the third order of the mixing mathematics. This all comes from the mathematics of mixers, but you don't need to know that part. That's not on the test. That's at a level above where we are. So third order products, and they're odd. Third is odd, the fifth and the seventh. But by the time you get that many orders away from the first order would be the mixing product that you desire to receive. Third order is the worst one because that's the highest level, closest in frequency, and those can mix down to be within the IF passband. Reciprocal mixing is where an adjacent RF strong signal mixes with the local oscillator phase noise and causes more noise or more signals to be mixed into your IF passband, thus junking up the intended receiving function that you're trying to achieve. So it's important to have a low phase noise local oscillator. Overload, putting very strong signals into your mixer, can cause spurious signals. It just messes up the operation of the JFET, the MOSFET, or the tube, whichever type of mixer you have, and overload will cause spurious signals to happen. Now let's talk about the dynamic range for a bit. Right here in the center of the screen, if you're looking at the screen, or in the lower center portion of the page as you printed it, looking down at the bottom, there's a theoretical minimum noise floor of any receiver, of any electronic component, is at minus 174. We'll leave off the units just because you need to remember the number 174, negative 174. Oh, look over here to the right, which is the lower right-hand corner on your printed page, for a logarithm scale review. We covered that back in, might have been even the technician class. I don't remember which one it was. It's been a while. But plus 40 is a very big signal. Plus 30 on a dBm scale would be 1 watt. You don't need to remember that, but that's where 1 watt is. Plus 2 is the answer to one of the questions. So it's a little bit over 0. 0 dBm is a milliwatt. 100 dB below that is 10 times below milliwatts, 10 to the 10th power below milliwatts. So it's getting to be really small. Minus 100 to 148 are the range of weak signal RF signals. So the 100 is just stuck in there to show you kind of where we're headed as we get to very tiny measurements on a dB scale. Minus 148 is an answer, and minus 174 is an answer. So there's numbers on this scale here that are answers to questions that we'll go over here in a little bit. Now back to the receiver dynamic range, just remember that minus 174 is a theoretical minimum noise floor. The signals you're receiving can't be below that, and in fact, they can't be below the actual receiver noise floor. The difference between the receiver noise floor and the theoretical minimum noise floor is called the receiver noise figure, and we abbreviate that NF, like Nancy Foxtrot. So all your signals that you're going to receive have to be above the receiver noise floor. And for a CW signal, a weak CW signal, the MDS, which means minimum discernible signal, is at minus 148 dBm plus the receiver noise figure. Now the question puts this as, what's the CW signal level above an ideal receiver? Well, an ideal receiver means it has no noise figure, but every receiver can't get down to, a receiver cannot get down to the theoretical minimum because it has electronic components and resistors, which all have inherent noise. So the minimum CW signal that you can receive is at minus 148 plus the noise figure. Other modulations have to have stronger signals than that. Sideband has to be stronger. It's on the order of AM. AM has to be a little bit stronger than that. But if you're going for very wideband modulation, like TV channel, the TV channel that would be 4 to 6 megahertz wide has to have a really big signal just to get over the receiver noise floor and have enough signal to noise ratio to give you a good picture. That's back in the old NTSC days. Digital, it's different, but don't worry about that. You don't have to know all that. Over here, I've shown you where the normal signal level range is, and there is a maximum that you can get to because you will induce distortion in your gain stages or in the mixer. And you can even overload an IF amplifier with strong enough signals. You'll probably overload the mixer before you start overloading your IF, but it can be done if the receiver design's not done carefully. There's a thing called the blocking dynamic range. A blocking dynamic range gives you the signal level causing a 1 dB gain compression. When you're measuring receivers, you're measuring how linear is the gain. What level of signal can you put through your gain stage to give you a linear output? That is, you increase the input to a gain stage by 1 dB, you expect a 1 dB output. Or you increase it by 10 dB, you want a 10 dB output. Blocking dynamic range is a measure of how much of where the signal strength where you're going to get 1 dB gain compression. That is, at the blocking dynamic range, you put in a 3 dB or 10 dB increase in signal level, you only get 9 dB out. And when that happens, you're at your blocking dynamic range, and that's important receiver measure. Let's see, the antenna noise goes to your antenna noise is compared to the internal receiver component noise. The internal receiver component noise sets the actual receiver noise floor, which is the noise figure amount above the theoretical minimum noise floor. Important to remember here, all these blocking dynamic range, the noise floor, the -148 for low-level CW signals, and the -174. Okay, let's see. I think we beat the IF to death. Let's move over to the right-hand part of the page. From the IF, and after some gain stages, you might even have 2 stages of IF filtering, which you can use to decrease the cost of the IF filter. And like John was saying, IF filters can be very carefully matched to the modulation bandwidth. HF receivers in particular, you have a way to select the IF bandwidth. So you can select it and make it very narrow for digital signals, FT8 or CW. I've seen them down to 300 hertz. One time I built a filter, an audio filter that was like 80 hertz wide for CW, and it had its own problems, but that's not to be covered here. After the IF, you get the detector. There's many types of detectors, and detectors are specialized for the type of modulation that they're going to receive. The detector is the same as demodulator. Demodulator is another name for detector. For an AM signal, you need a diode detector that rectifies the AM, because you remember AM signal has the carrier frequency plus 2 sidebands. So you've got everything there you need if you just have a simple diode. So the function of the IF gain stages is to provide you a very large amount of gain so you can drive this diode and get the rectification for the AM signal, and out comes AM. And it sounds great. Everything is, all the frequencies are aligned. The thing about product detectors for single sideband and also CW, I've left off CW right here, but a product detector is used for sideband and CW. And there you're adding back the carrier in relation to the single sideband that's transmitted. Well, we'll get into that distinction when we get into transmitters and modulation. There's a chapter on that too. So the product detector is used for single sideband and CW. For FM, the detector is called a discriminator because what it has to do is to take the changes in frequency, or if it's a phase modulation, the changes in phase, and create the audio signal back out of that, audio or visual signal, whichever one you've got modulating that FM signal. Because let's see, where was it? We used FM TV. There's a class of amateur TV that uses FM modulation instead of AM modulation. And so it'd be a discriminator, but it has to be a very wide bandwidth to be a picture. Now there's one neat characteristic that I used one time. It's called the capture effect. And that's when, back in the early stages of the International Space Station, that had to be about 93 or 1994, where you could use, but that's before the space groups, ARIS took over to make school contacts with the space station, and they had to schedule everything, and it got a mess when they took it over, which usually happens when you get organized groups involved. But an individual ham could use an FM radio, talk directly to the International Space Station. And there's one thing you use there is, if you're the biggest signal, the largest amplitude signal that gets to a discriminator, you win. The largest amplitude signal on the same frequency, it doesn't cause distortion in the output. It just takes over the discriminator and it wins. That's the output, that's the audio that's coming out. So I hooked up like an 80-watt FM amplifier on the output of my handy-talkie, and I used the capture effect to where I was the only signal that got through to the space station. No, it's not cheating. I just used what I knew about discriminators and capture effect. The largest amplitude that hits the discriminator that's coming out of your IF will capture that discriminator, and its audio is the one that gets demodulated. Now there's another extra little circuit that you use called the de-emphasis circuit that you put in your receiver that corrects the audio amplitude response in case your signal you're receiving comes from a phase modulated transmitter. A discriminator can detect both frequency modulation and phase modulation, and you use this de-emphasis circuit. And the example in the book has a cutoff frequency just above, it was like 2.8 or almost 3 kilohertz. So it didn't have any ill effects on the audio. It just straightened out the audio response so you could detect phase modulation. Okay, now we come out with our CW and our audio. You can hook that to a speaker, send it to your headphones, and listen to it. But there have been some recent developments with DSP audio filtering. There's some very excellent filtering you can get through DSP filters in the audio range. Audio DSP filters are called adaptive filters. That means that the DSP has software in it that adapts the filtering to the different types of noise that can be coming through the audio channel that comes out the detectors. The adaptive filters in a DSP remove broadband noise, ignition noise, and power line. All these type noises will be removed by adaptive filters in DSP. Another neat thing you can do with DSP filtering, and a lot of modern radios, HF receivers have this built into it, is a notch filter. Now on my HF receiver, I can move that notch filter to remove adjacent CW signals I don't want to listen to, or it can remove the whole CW signal that you're trying to get. So you have to be careful using the notch and get some practice with it before you turn it on in the receiver, because it could also remove the CW signal. Because it's so narrow, it can remove that whole CW signal. There's another type of filter that can be in DSP filters, is a noise blanker. There's other types of noise blanker, and some of them appear in the IF string, but the noise blanker can be an external audio filter that removes wide bandwidth signals. Now, wide bandwidth signals are usually the ignition type noises. Impulsive noise is the technical term for it in engineering. Impulse noise, which is just a click, a real short pulse, makes wide bandwidths when you feed them through filters. And a noise blanker can remove those wide bandwidth signals. Let's see, what haven't we talked about? We'll do that in a second. Back over to the left, let's talk about interference sources. Atmospheric noise on the low HF bands, everybody's heard that. Static crashes from lightning is the biggest culprit. There used to be a thing called a woodpecker that the Russians were using for HF radio for radar, over the horizon radar. That's an interesting topic all in itself. You can research on your own. It's called the woodpecker. And there's atmospheric noise, there's galactic noise. When you get up into microwave operation, you have to figure how much galactic noise from the galaxy you're getting. If you point your, well, we won't go into that. Anyway, there's lots of atmospheric noise sources. On HF bands, the low HF bands, it can be greater than the internal noise in your receiver. Let's talk about all the interference sources. You can have, and probably nowadays usually have, a personal computer sitting right beside your radio. And if your coax connections from your antenna are not securely tightened to your radio, they can pick up the interference coming out of your PC. I've heard it. Some of you may have had experience listening to that. They're described as unstable signals at specific frequencies that come from your personal computer. There are AC line interference sources. AC line interference sources can come at specific intervals, such as a thermostat. That may be a very long interval, but it'd be an interval anyway. A doorbell, when you ring a doorbell, you can get some AC line interference. Or advertising displays. Neon signs is what this would be referring to. And all these choices are correct for AC line interference that can come into your receiver. Another type of receiver of interference to your receiver you can get is when the AM broadcast band signals meet up with corroded metal joints, such as your downspouts on your rain gutters around your house. On metal chain link fences would be bad for this. If you live, or if your antennas are close to an AM radio station transmitter, and you've got any kind of corroded metal joints or a chain link fence or gutters on your house, you could have interference from this. It'd be broadband. You might be able to hear some of the AM audio signal coming through your IF from this interference source. Now, how do we deal with all those interference sources? First thing, let's look at where they fall in the receiver dynamic range. Some of them will be as strong or stronger than the modulation that you're trying to receive. So those interferences, just noise, can have amplitudes up here in the normal signal level range. The woodpecker was way above that. The woodpecker could almost cause distortion Even in the middle of the country in Texas, the woodpecker was a horrible distraction. Back in the late 80s and 90s, it was a mess. It's mostly gone away now. I haven't heard it recently. And even one time I heard it, I was not even in the ham band listening around. Sometimes I just like to listen around the shortwave bands and see what's out there. So I'll get curious and find out what else is out there. I heard the woodpecker going strong that day. And that was early 2000s. Well, I guess it's been 15 or 20 years. So that could be quite a long time ago. Another thing you can do for all these interference sources is put in your attenuator. Up here in the front end of your receiver, if you attenuate the interference sources. Now, what's neat about this is the attenuator is a flat frequency response. That is, it has no frequency response inherent to the attenuator. The frequency response is all in your front end preselector. But if you switch in some attenuation, it can reduce these noise sources so that they're not strong enough. See, the noise sources you would expect to be down on the skirts of your filters. Both the preselector, the roofing filter, the IF filter, they would be slightly off frequency, but they can still cause descents, that is, get your amplifiers to lose some of their gain. They can cause your mixer to have extra mixing products get through your IF frequency that goes straight to your detector. So the whole point of this receiver is to maximize the signal strength of your modulation getting to the detector and minimizing the noise. So you use the attenuator to do that. Let's see, the only section here we haven't covered is the software-defined direct digital conversion receiver. This is the newfangled modern stuff besides heterodyne radios is a software-defined radio. Now, some software-defined radios have some filters and mixers in it, but then those would all send your receiving antenna signals to a high-speed ADC. ADC is an analog to digital converter. But there is such a thing as a direct digital conversion radio where the antenna would hook straight to a high-speed ADC. And with modern advances in integrated circuits, there are that fast of analog to digital converters that can work on the HF directly. Now, when it does that, the ADC will send its signals to a DSP. Now, here, DSP is one block. However, don't let that fool you, because the design of DSP and signal processing and filtering can take up pages more than what this one page is of block diagrams for receivers. DSP, signal processing, and filtering can be very extensive, and it's all written in computer language, computer code. So a DSP is a digital signal processor. It's a souped up microprocessor with lots of memory, lots of channels to handle high-speed digital data, and that's what's coming from the ADC, and it does specific things with that in order to make software-defined radios work. Out of the DSP comes your audio, CW, your FT8 demodulation, and a lot of DSPs, even the DSP can handle the demodulation of the FT8 running. I mean, the DSP has to run in a computer, and so that computer operating system can handle the software required to decode FT8. So this is, the DSP block is a computer, but don't let that fool you because the software is very complex. So the direct digital conversion receiver depends on the high frequency, high speed, high frequency ADC, analog to digital converter. The dynamic range of this receiver is set by the number of bits in the ADC. And the DSP has to be matched to the number of bits in the analog to digital converter. So the number of bits sets the dynamic range of this receiver. There's a trick you can do to signal processing in a DSP is to use dither. Now, dither means like a small amount of noise that's added to the ADC output. And what it does is it tends to kind of smooth over the ragged edges of signals before they hit the DSP. And that's an advantage for the signal processing in DSPs. That's called dither. It's by adding a small amount of noise to the converted signals from the ADC. SDRs are susceptible to input signal overload, just like the other receivers, just like when you get a very strong signal coming into this receiver that's greater than the ADC reference voltage. Now, an analog to digital converter can only convert signals of specific voltage, specific magnitude, and that limit is the ADC reference voltage. So when you get an input signal that's that voltage that is greater than that voltage, you will cause signal overload and you're not going to get anything through the ADC. Now, SDRs have these type of problems. This is a very short list. There's other problems they have, but this is what will be covered in the extra class exam. Has anybody got any questions on this diagram before we go to the questions in the question pool?
In the log review there at the bottom, Wayne, which ones are answers for the test so I can just highlight them on your?
I know the 174 that's the theoretical minimum noise floor. The 148 that's the CW minimum detectable signal in a perfect receiver. And there might be another one on here. We'll get to that when we go through the question pool.
Thanks.
But I would recommend you keep this chart handy. If you printed it, is why I recommended to print it. And we'll go through the question pool and you can highlight things, make notes on it as you'd like to. Any other questions? No questions? Okay, then let's go to, I'll keep this, let's see, I have to do something to rearrange my Zoom controls so that I can do a new share. And I want to share the question pool. Well, I have to find the question pool first. That will be in the File Explorer, if I can get to that part. Hello. Well, I had it. Let's see, it's in this folder. Get this out of the way. We have receivers and great filters. I thought that's where I downloaded it. Okay, well, let me go get it from the email. I got it in the email just like you got and thought I downloaded it. Sorry, I didn't put it in the right place. Oh, I know where it is. It's in the downloads. I didn't move it. Desktop. Downloads. Here they are. All right, now we got it. Now I can share that window. I'll have to start over. Okay, we're going to share. No, this one. Let's see if that comes out right.
Got it.
You see it now?
Yep.
Okay, let's make it bigger so everybody can see it, so I can see it. There, now I can see it. That's even better. All right, is that too big for anybody's receiver? Yeah, screen, display. I guess a LCD display is kind of like a receiver, isn't it?
That's coming through my filters just fine.
Okay, great. Okay, we're going to start off with, what is the term for the suppression in an FM receiver of one signal by another stronger signal on the same frequency? If another stronger signal is on the, where'd it go? Is on the same frequency, what's that called?
Desensitization.
Capture effect.
Capture effect.
No, this is the capture effect. This is in an FM receiver. A stronger signal is going to take over the receiver. That's the capture effect. At times it's useful. So if you operate FM a lot, you need to remember that one and have a big power amplifier standing by.
That's when you achieve using your 80 watts.
That's right. That's what you use 80 watts FM for. You take over a receiver. It's called, what's it called? Capture effect. Okay. You got to remember capturing the FM channel. What's the term for the reduction in receiver sensitivity caused by a strong signal near the received frequency? Reduction in receiver sensitivity is the key to this.
Desensitization.
That would be called desense.
Just
That's
thinking
right.
it's got the same word in the answer, almost.
Close, yeah. You're desensitizing the receiver caused by the strong signal near the received frequency. Which reduces the likelihood of receiver desense. We want to reduce desense. What can we do to do that? We're going to decrease the bandwidth of the receiver. One of the filters in the receiver string needs to go down so the close-in strong signal will be attenuated off the skirt of the filter. We're going to decrease the bandwidth. It says RF bandwidth. Decrease the RF bandwidth, the preselector or the roofing filter, one of those. What is the frequency discriminator in an FM receiver? That's the detector. Discriminator is the detector for an FM receiver. What is de-emphasis used for in FM communication receivers? What was de-emphasis for?
Phase modulation.
To be compatible with transmitters doing phase modulation. An FM receiver can receive both phase modulated and frequency modulated signals. But de-emphasis is for the compatibility with phase modulated transmitters. What transmitter frequencies cause an intermod product signal tuned to 146.7 when a nearby station transmits on 146.52? Oh, we might need to look at the book. Everybody got the book. This is on page 124, and the explanation is on the top of page 125. So this is the intermodulation product signal when two strong signals, nearby transmitters, are close to your 146.52. Now, the way you figure this is it takes twice the frequency of one of these and subtracts off the other. And when that difference hits your IF, that's when you've got intermod product signal that's going to bother your receiver. Let's see, in the book, it takes, what does it take? If you take twice, 2 times 146.52, which is where you're receiving, and subtract off the other frequency, then you get the on channel signal. So this combination that works is 146.34 and 146.61. And it's all a matter of the nonlinear mixing going on in your mixer. Does everybody follow that? No? Okay, this is, no.
This is-
What I did was,
Let's use the whiteboard. I'm going to use the whiteboard. We're going to draw on the whiteboard. So you'll have to, let's see, I need a squiggly line here so I can draw. Let's see, what type of color I want to use. How about black? Let's use a black wide marker so it looks like that. Okay, that'll work. Everybody can see that line? So what they've done is you want
you're gonna
2
take
times
146.52 plus 146.70. Is that how you figure it out? And then divided by 2.
So somebody have a calculator handy? We'll just work through this one.
Yes, hold on, I got it.
Somebody's got to have a calculator or something easier to use than the one in your cell phone. Those are wonderful, but I like calculators. So what does that come out to be?
293.04.
293.04. This sure is handier when you're in person and have a whiteboard.
you could type this using the text.
I could. You can blame it on K5GD. Okay. So what's the other?
Divide that answer by 2.
Well, we just multiplied it by 2 to get 146.52. We have to
I'm sorry,
subtract
subtract 146.7.
146.7. He's running the calculator.
And you get 146.34.
146.34.
Well, that's probably not going to bother us. Let's take another frequency. Let me get my whiteboard eraser over here. All right, let's start over. Whoops, no, this doesn't work like paint. I'm used to drawing in paint. Okay, I can do that. Now then, back to the pencil. Let's do 2 times 146.7. That's really where we're receiving. I don't know why they had that other example. 146.7 is where the radio's tuned right now. So what's 2 times 146.7?
293.4. 293.4.
293.4. So if we subtract from that 146.34. You know, we really ought to be doing this in Excel as a spreadsheet. But anyway, this is more fun. All right, then what do we get?
147.06. That's not right.
Yes, it is. That's right.
That's what comes out, right?
Yeah.
Oh, no, we didn't do that right.
We didn't do that right.
You're right. That was wrong. Okay, the nearby station is on 146.52. So do 146.52 again.
Times 2.
Times 2.
293.04.
All right, that's 293.04. Now subtract off 146.34. What do you get?
146.7.
We're still doing something wrong. Don't we have to add those two together, then divide them by 2? That's what the book is doing.
Well, he rearranged the equation.
Well,
So
if you,
I'm confused.
Subtracting 146.7. You're using the same frequency both times.
You're right.
if you take the difference between the 146.7 and the 146.52, the difference is 0.28 or 280 kilohertz. Okay.
Mhm.
If you take half of that and subtract it from the 146.52, you get 146.34, 14 from 52, which is 1. And if you add that to the 146.2, you get 146.68.
No, that's not going to be right either. Okay, let's start over.
No, I'm adding it wrong. 5.2 and 14 would be 64. Yeah.
All right, then we'll do the example in the book. So the intermod frequency I didn't want to get into the mathematics, but looks like we've wandered there. Sorry, is twice one signal minus another. It doesn't matter which frequency you call 1 or 2. It's mathematics. So he wants to rearrange this and figure out what F2 is, or F1 in this case. So 2 F1 equals the intermod frequency plus F2. So I've got 1 and 2 switched from what the book has. Anyway, it'll work out. So if the receiver's tuned to 146.7, so if you cancel the 2 on this side and divide all this by 2, which is what we're going to do. So if the interfering signal is 146.52, and you add the channel you're tuned to, what was that, 146.7? Somebody add those for us. 146.52 plus 146.7, and then divide by 2. That should come out.
That comes out to 146.61.
Okay.
Is the answer shown?
So if you have two transmitters on the, air, one on 146.52 and one 146.34, intermod distortion will give you a signal on the receiver frequency of 146.7 is what we're saying.
Yes, that's right.
And the same is true with the 146.61 transmit frequency.
That's right. So there are repeater outputs that will mix because of intermodulation products to give you signals that are in band, that is, come through your IF filter. So you have to watch that about, especially on 2 meters where there's so many high-powered transmitters from repeaters that will do that to you. And here's a prime example. It said the questions: what transmitter frequencies would cause an intermod product signal? That means to give you a spurious signal in a receiver. You're listening to 146.7, and then you've got three signals come up. 146.34, that's the input to a local repeater. 146.61 is the output of a local repeater, and 146.52 is the national calling frequency for FM. And so you get those 3 on, and you'll hear it come out 146.7 where you're trying to listen. Now, I don't know why you'd be, yeah, I got that upside down. Okay, so that's the answer. If you come across this question, you see 146.61 as one of the frequencies and one of the answers, that's the answer. Or you can sit there for 15 minutes fiddling around with your calculator and trying to remember what the example was in the book.
It's easy to calculate. If you just add the 2 together and divide by 2, that's one of the answers.
Okay. Right. And the other way is you take twice the 146.52, subtract off where you're listening, and that's the other frequency in there. But see, the problem with this question is 146.34 occurs in 2 answers, but 146.61 is only in 1 answer. And the numbers will not be changed on the test. That's the guarantee from the rules of the VEC. You can't change the numbers or the wording in the questions of the question pool. They have to use the questions directly from the question pool. So that's the thing you need to remember about taking the test. Let's get back to something useful. Okay, so if you have this question on your test, it's not even guaranteed this one will be on the test. But if you do, you have intermod product signal is what we're talking about. The receiver's at 146.7. Another transmitter transmits on the national calling frequency, 146.52. Pick the one that says 146.61. Let me rephrase my answer. There's the answer. Now, ever what calculation you want to do that, go for it. The only catch is you can't store that number in your calculator. You can figure it out in your calculator, but it can't be stored. That's the rules of giving tests. I let my ARRL VE certificate run out. I still got mine active with W5YI. So I've given tests. So I've had to explain all these rules to people taking tests. So I've done it before. Let's move on. Any questions? How about a break before we move on? Seems like a good time to have a break and clear our mind of this question. And
Yeah, we're about halfway through
we about
our
halfway
time
yet?
slot, so this is a good time to break.
Yeah, you got a
We're
couple
halfway
of,
through no, we're not halfway through the questions yet. We've still got lots of questions to go.
Yeah, we're on number 7 or number 6 of 72 questions.
Okay, so how about a 6 or 7 minute break, which will put it, depending on how your sundial is today, at
35 minutes after the hour.
35 after the hour. Let's do that. I'm ready for a break.
Yeah, the key in this intermod question is the difference in the two frequencies, which is 18 kilohertz. And if you take 18 from 146.52, it's the 146.34. And if you take the one that's halfway between the two, it's 9 kilohertz, which is the 146 above the 146.52, which is 146.61. Which I find an easier way to do that personally. Break time.
John Wayne,
I'm back.
John Dale, Lincoln, Nebraska. I just want to tell you how much I really appreciate your diagram. Your
You're welcome.
diagram of the receiver. It's excellent.
Thank you. I hope a lot of people can get some good out of that. We have a place on our North Richland Hills Ham Club webpage we can post things. I'd like to get it posted up there and even do a presentation one club meeting.
Yeah,
I think a lot of people could get some good out of that.
this is beautiful.
Anyway, that's a lot easier for me to look at that than it is to go through 20 pages of questions.
I know what you mean.
And then we'll talk about the questions too, and you can see how the question relates to each part of the diagram.
Well, I can see by going through the questions, which I've done so far, that it all falls together.
Yes, it'll all come together to make a receiver, but it's easier to see when you can get the block diagram written down.
Yeah, absolutely.
So you're welcome to take that page and give it to all your friends and do whatever with you want to. If you want to show it to your ham club, go for it. It's free.
Will do her. Thank you.
That helps me out a great deal with all the radios and everything.
What was that again?
So that helps me out a great deal. I now completely understand how the radios work.
Oh, good. Well, then that's one purpose fulfilled from it. Because until I got started working and drew out all these blocks in a string like that, I didn't know how all the pieces fit. And that was from a college education. So you sometimes you just got to sit down and look at the big picture and then start filling in the details.
Yep.
Well, good. I'm glad you got some good out of it. Thank you for your comments.
I think we all got some good out of it, John. I really do.
Agreed.
There's a lot more to receivers that you could fill in. Some other, well, soft SDRs, software defined receivers, can be a whole lot more to it. And then with those, you have to get into the design of the software and the digital signal processing. I've studied some of that, and that's a whole nother subject in itself, besides RF receivers.
Well, software defined radio is just black magic. There's no way anybody can figure it out.
Well, they used to say super het receivers were black magic, but here it is laid out in black and white in front of you. It's not black magic. And the signal processing in DSPs for the software defined radios is not any more mystical. It's just different stuff.
Yeah.
And you have to know computer programming to do it. So it's some extra bits to it, but
Yeah, part of what I don't understand in the software-defined radio is what that little chip in the dongle is doing. And that's what you talk about as far as the ADC, analog to digital conversion.
okay. Well, maybe we should have a club presentation on that because there's several people that have software-defined radios. We can go over that too.
Well, I am one of those. I have 2 of them actually.
Oh, okay.
And one of the reasons I'm off the air right now is I'm trying to get the software-defined radio to work with a Raspberry Pi 4 instead of the big laptop that I've been using for it. So I can use the laptop for logging and such stuff instead of for receiving.
Right.
I use it. Like I said, I use the SDR. Well, I'm going to be pulling information from my weather sensors that's run at 433 megahertz.
Yeah, there you go.
Well, the thing I find fascinating about the software-defined receiver is that you give me a frequency that some part 15 thing device is using, like a wireless microphone at church. You give me the frequency and I can tune in and analyze the signal and see whether it's spread spectrum or just pure analog FM or what.
Or some other coded digital method.
Yeah, and I get to watch all of my neighbors' garage door openers and other stuff on 433 megahertz. You put that thing there, watch that thing, and psst, 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 the signal comes through, and there you got it.
You know when your neighbors are coming home.
Well, the other thing is that you can record that and then retransmit it and open the garage door.
Yep, you can.
Don't they have random codes now in garage door openers where you got to have the random code as well? No.
Well, if you're just copying the signal that they're sending from their car, from the controller that they're using to open the garage door, if you copy that signal and you retransmit it, you record it and then you retransmit it, it's got all that access code in it.
Did not know that. I'm gonna be more. I can look around me next time we go to open up my garage.
And if you have the frequencies for the Bluetooth stuff that the automatic key fob things for your cars are there, and you record that off of an SDR receiver and retransmit it, it will open the car doors.
Yeah, my key fob for my car is encrypted.
It doesn't matter because what you're copying and what you're receiving is the encrypted code.
Ah, you're kidding me.
No. In fact, there are criminals who use the software-defined radio record process. Like I say, it's black magic. All you have to have is that little burst of radio frequency stuff received and recorded off of software-defined radio.
We don't have any criminals taking this class today, do we?
All hams are criminals.
Right.
There's that part of me that wants to experiment with that just because of my friend Bob. I have a friend who the friendship is based on rivalry, way back in the 60s, well, in the 70s, he was at grad school and I visited him, and he had this brand new Ford LTD, and I said, I want to drive that. And so we run out to the car, and he says, you'll need the key. And I say, no, I won't. And I reach in my pocket and get out my Mustang key and put it in the lock and open the door on that car. His mouth dropped tremendously. I had no idea that that was going to work, but it did, and that was scary. Anyway, enough of that. We need to get back because we're going to be tight on time.
Does that mean his key? Does that mean his key worked in your car as well?
I had to jiggle mine a little bit to get it to work in his. I don't know. We never tried that. I wasn't going to give him the suggestion.
There you go.
But that was one of those moments that the memory of it I cherish forever.
John, I'm afraid you can't break into my car with your software-defined radio. It still takes a key.
Yeah, if you do it with a key and do not transmit a signal, there's no way the software-defined radio can do it. I don't know what frequency car key fobs are on, but I might take my key fobs and kind of look around and see if I can find it. That'd be interesting.
Yeah, you can find it. Try 400 something range.
Well, I'd start with 433.
Okay.
Because that 1 megahertz in there and that ham band has got prolific part 15 stuff.
Mm-hmm.
Anyway, I'll shut up.
All right. All right. In the book, if you're following, we're on page 125. If you're looking at the screen, this is the next question. One of these things describes problems caused by poor dynamic range. What is poor dynamic range related to? Strong adjacent signals and cross-modulation, desensitization. Here's desense. Poor dynamic range has the problems of cross-modulation and desense from strong adjacent signals. What does a receiver noise floor of minus 174 represent? That's the theoretical, and the mathematical definition is a 1 hertz bandwidth in the input of a perfect receiver at room temperature. 174 is the theoretical noise floor in a 1 hertz bandwidth.
And does it really have
That's
to be
the
a room
perfect-
temperature, or did they just throw that in there?
That's the definition, because the noise in electronic components is very temperature sensitive.
Okay.
The 1 hertz bandwidth is part of the definition. I think we'll see that later. If we're not, I won't confuse your brain. What is the MDS of a receiver? Minimum discernible signal. It's the smallest signal that it can receive. And there's a mathematical definition to go with that. Let's see, page 126. It doesn't give you that, so I won't either. But you can Google MDS, receiver MDS, and it's very interesting.
Didn't you
Minimum discernible signal.
Wayne, didn't you skip a question? Or did I miss it?
Did I? I
406,
might have skipped it. Sorry.
E4C06.
Oh, I'm sorry. I skipped that one. It's not in this list, so I'm sorry. I skipped it. Okay. The question that's not in the list is in the book. The CW receiver. Thank you for telling me that. The CW receiver with AGC off has equivalent input noise power of minus 174. What is the level of an unmodulated carrier input to this receiver that would yield an audio output SNR, signal to noise ratio, of 0 dB at a 400 hertz noise bandwidth? Well, this is the reason why we said it was a 1 hertz bandwidth definition for the perfect receiver, the minimum receiver noise floor, is because the noise, the signal strength in a receiver depends on the bandwidth of the channel of your IF filter. And the answer to that question is the minus 148. And the explanation of that is it's 174 minus 174 plus 10 times the log of the bandwidth. And that is we specified in perfect receiver. So that's why on my chart diagram, I said the CW minimum detectable signal is minus 148 plus the noise floor. So the question reads, a CW receiver has equivalent input noise power of minus 174. And you see in minus 174 right there, you think theoretical minimum perfect receiver. So what's the level of the unmodulated carrier that would yield an output signal to noise of 0 dB in 400 hertz bandwidth? So it's 10 times the log of the bandwidth. Oh, it's there. 10 times the log of the bandwidth, which turns out to be minus 148. So that's how you figure that. Sorry, this question was not in my list. I'm sorry, I skipped that one. So that's where the 148 CW MDS comes from. It's that question. So when you see it on the test, the question asks, what's the signal level to get the same signal as you have noise, which is a difference of 0 dB. And it's because you increase the bandwidth from 1 hertz to 400 hertz, and that's minus 148. Just looking at the 4 answers, it's the highest signal in that list. The wrong answers are 174, which is the perfect noise floor, 164, 155, and 148. So you have to have the minus 148. You don't need to calculate it. You just look for the biggest signal in there, which is minus 148, which is why I put that log review in there to remind you that minus 148 is a bigger signal than minus 174. And I didn't put in the incorrect answers in my log review list. Okay, that's the answer to the question of which numbers in that log review are answers. It's minus 148.
I don't want to beat this to death, Wayne, but how did it come up with the minus 26 dB from the log, from the
What?
10 times the log?
The logarithm of 400 is
Is 2.6.
2.6 times 10.
Okay,
And so 10 times that's 26. Yeah, add that to 174, so you get minus 148.
gotcha. Okay, thanks.
Yep, that's it. What is the MDS of a receiver? We already did this. Oh, that's because we skipped that one. Sorry. All right. Everybody knows that's minimum discernible signal. Which of the following noise figure values is typical of a low noise UHF preamp? Oh, that's why the 2 is in that list. 2 dB is the noise figure of a low noise UHF preamp. That means that preamp adds 2 dB noise to any signal you're receiving, which at UHF is pretty bad. That's a pretty bad preamp. A good preamp would be a half a dB, but noise figure values are always positive. And if you had a preamp with 44 dBm noise figure, you couldn't hear anything through it. So 2 dB is noisy for a UHF preamp, but that's the answer.
Well, there's another piece here. C and D are decibels reference to millimeters or milliwatts. dBm is decibels reference to milliwatts.
Right.
And the noise figure is not going to be referenced to milliwatts. It's going to be something that's added to the noise floor. So the 44 dBm is meaningless in this question, and the minus 20 dBm is meaningless. The 2 dB is really unless you've got it cooled to almost absolute zero, 2 dB is not a bad thing. 10 dB noise filter or minus 10 dB noise filter is the preamp removes 10 dB of noise.
No,
And
can't do that.
you can't remove noise.
No, noise is there and it only adds.
That's correct. So that's the way you figure that question. dBm is a reference to a particular point, and 44 dBm is 20 watts of signal.
Yeah, that doesn't make any sense for this question.
Yeah.
Okay. Thanks, John. What's a crystal lattice filter? We talked about crystal lattice filters. Anybody remember? It's not a power supply. It's using lattice-shaped quartz crystals. What? That's not even right. It's not the crystal that's shape of a lattice. It's the circuit that you connect quartz crystals in that's a lattice. It's like a...
Yeah, the answer to this one is D, because of the very narrow bandwidth and the steep skirts.
Right.
The fact that it uses quartz crystals is the thing that gets the crystal in it.
Yeah, you don't...
And if you looked at the schematic, you would see why it's called a lattice filter. It has quartz filters in series with basically with RF chokes at each point between the filters. And it looks like a ladder type thing or a lattice in a garden.
Maybe I'll include a picture of that in our links we'll send out today, because I kind of intended to do that and just didn't. So I'll send a picture of a lattice filter or a reference to it or something in the list we send today. A lattice filter is narrow bandwidth and steep skirts. That's how you make good IF filters.
And a lattice filter uses more than just one quartz crystal in the filter. You can do a filter with just one crystal.
Yes. Narrow bandwidth and steep skirts for the filter. Which of the following factors has the greatest effect on the bandwidth and response shape of a crystal ladder filter? How do you make the best crystal ladder filter?
Aren't they frequency based? So A is the only real answer, right?
A is the only real answer, yes.
Now, if you have crystals that have slightly different frequencies, you get a broader bandwidth in the filter, and the slope, the skirt slope is still just as sharp.
Yes. Which of the following describes the receiving filter's ability to reject signals occupying the adjacent channel? So we want to reject the adjacent channel. That's that shape factor. That describes how steep the skirts are. We talked about that in the definition of the characteristics of the filters. Shape factor. Every filter has a shape factor. IF filters, you want to have a very sharp shape factor. And that's what gets rid of your adjacent channel. Because your mixer is going to mix the channel 25 kilohertz away or even 3 kilohertz away just as well as it does the signal you're trying to listen to. It's just that the adjacent channel is going to be right next in frequency to your IF filter. And when the skirts are broad, that means you've got a broader shape factor. You're going to get some of that energy passed along to your detector, which is going to mess up the signal you're trying to
It might help to, in this one, John, Wayne, to note the definitions of other. The passband ripple is the variation in the attenuation level at the peak of the filter in the passband.
Right.
I have no idea what phase response is. Noise factor is a term that has to do with the level noise floor. So the shape factor is the only one that really makes sense here.
That's right. Yes. Which filter type is described as having ripple in the passband and a sharp cutoff? Which filter had ripple in the passband?
Isn't that D?
Yes, Mr. Chebyshev. Now, Butterworth filter.
I think Chase whenever I hear that.
Yeah.
The Butterworth filter is known for and used for a very smooth passband response.
I use it
LC
on my
filters,
pancakes.
yeah, it's good on pancakes too. Except, LC filters and op-amp filters are all ripply in the passband, but the one that's described as having ripple in the passband is the Chebyshev. LC and op-amps don't have to have ripple. An op-amp filter is just how it's made. I made Butterworth filters in op-amps. So the op-amp filter isn't a type of filter, it's just how it's made. Active LC filter is LC liquid. No, not liquid. Inductors and chokes, inductors and caps.
And I have a problem with the concept of an active LC filter because you just got two passive elements in the filter. And then the C is a problem because an op-amp filter is not a passive filter. It uses the active op-amp characteristics to do the filtering.
Yeah, an op-amp's not passive for sure. Yeah, those answers are all messed up.
The only two that could possibly make any sense is the Butterworth of the Chebyshev, and if you remember Chebyshev as similar to Chevy Chase, you can remember how funny it is, and then you can see the ripple.
Didn't he have some ripple? But if you think of Butterworth, think of melting butter. Butterworth melts butter melts and it's all smooth and gentle in its slopes.
Yeah, I may select Butterworth depending on what time I take my test. If I'm hungry, if it's in the morning before breakfast, then it's going to be Butterworth.
No.
If you miss this question on the fact that you're hungry for buttered toast, you deserve to flunk.
Yeah, no kidding.
Yeah. All right. What are the distinguishing features of the elliptical filter? Remember what we said about elliptical filter? Notches in the stop band. Yes, it has a sharp cutoff also, but it has notches in the stop band. That's elliptical. Okay. Why would a direct or flash conversion A to D converter be useful for SDR? Direct or flash conversion ADC? Because it's very high speed. It's the only thing that fits. No, it's not all choices either. Flash conversion ADC is very high speed, so you can digitize high frequencies. An A to D converter has to be high speed for high frequencies. Which of the following has the largest effect on an SDR dynamic range? What we say was the software-defined radio dynamic range.
Number of bits.
Analog to digital converter.
In the ADC. ADC sample width in bits. Right. The software-defined radio depends on the characteristics of that analog to digital converter. So you've got to have that. That's got to be the best component in the radio. What's an advantage of having a variety of receiver IF bandwidths? Why would you want to have different IF bandwidths? So the receive bandwidth can be set to match the modulation. Maximizes signal to noise ratio and minimizes interference. Noise figure has nothing to do with bandwidth or matching modulation type. Noise figure is noise. This is receive bandwidth.
I think of this question in terms of my 857D trying to listen to broadcast radio. The IF pass band, the broadest that I have is 3 kilohertz. And so when I'm trying to listen to AM, I only get 1.5 kilohertz of usable audio.
That's not a lot.
No, it's not. You can barely figure out what they're saying in that bandwidth.
So you're not matching the received bandwidth to the modulation.
Right. I can go from single sideband to CW by changing filters, but I only have 2 filters in the radio.
Oh. So you don't have one matched for AM?
I do not have an AM filter in it.
Yeah, that'd be a problem.
No, but it's a good way for me to remember this question.
There you go.
Which is why I interjected it.
Okay, good. Thanks, John. Let's see here. Why can an attenuator be used to reduce receiver overload on the lower HF bands with little or no impact on signal to noise ratio? It's because atmospheric noise is generally greater than the internally generated receiver noise. because you can reduce the atmospheric noise and it won't affect what you're listening to on the lower HF bands. So I use that quite often. In fact, I keep the attenuator on my receiver most of the time because I don't want my neighbor up the hill to be blasting my radio. And he does sometimes. I had another neighbor that was another block the other way to the west, and but he's gone silent key many years back. But one time we were talking, I caught him on the radio, and we were both pegging our S meters, and he said, "I always wondered what it sounded like to talk to somebody 2 blocks away." Well, now you know. So blast your S meter. So that's when I needed an attenuator, but the radio I had back then didn't have an attenuator.
Yeah.
So that's atmospheric noise. How does the narrowband roofing filter affect receiver performance? The narrowband roofing filter does what? It improves dynamic range by attenuating the strong signals near the receive frequency. Because you want to keep strong signals away from your mixer. So you put this roofing filter in front of your mixer and it improves the dynamic range. That means you can hear weaker signals without the strong signals attenuating. I guess we never did define what dynamic range did to you. Dynamic range means the difference between small signals and large signals. And a roofing filter attenuates the strong signals. That's how you improve your dynamic range. And a roofing filter does that. Which of the following receiver circuits can be effective in eliminating interference from strong out of band signals? We want to eliminate interference from strong out of band. Which one did that? The preselector.
Yeah, the front end filter.
Front end filter. Some people call it front end filter. Some call it preselector. I called it preselector because that's the first part of the radio that I was working on when I was building FM communication radios. Okay, strong out of band. Which of the following choices is a good reason for selecting a high frequency for the design of the IF? You remember what we said a high IF frequency would do? It helps the front end filter eliminate image responses. Circuitry should be filter right there, but he wanted to confuse you. The writer of these questions is good for that. I don't think Gordon didn't write all the questions. He just put the book together. You can read about how the question pool's put together. But anyway, that's intended to trip you up. So the high frequency for the design of the IF, the high IF frequency gets rid of image responses because that puts it farther out away from the pass band of the front end filter preselector. What transmit frequency might generate an image response in a receiver tuned to 14.3, 20 meters, that uses 455 kilohertz? Well, let's see, what did we say about images? It's twice the IF frequency away from the receive frequency. So what's 2 times 455? That's 910 kilohertz.
910.
Okay, so it didn't say where the IF was relative to receive frequency. This is our receive frequency at 14.3. So which of these frequencies listed is 910 kilohertz away? Oh, here, D. 15.2 megahertz is 910, which is twice the IF frequency off of the receive frequency. That's
Yeah,
what
if there was another image frequency, if it was the local oscillator was not above the 14.3 but below it, the image frequency would be 910 below, which would be 13 something.
13.39.
Yeah,
I guess I don't have my calculator handy.
I think that's correct, but that 13.845 is not it.
Not it. No, that's not it.
So are you saying you would subtract the 910 to get the other?
It depends on where your local oscillator frequency is. In this example, the local oscillator frequency is above the 14.3, and it's going to be 455 kilohertz above the 14.3, which is 14.455. And then the image frequency is another 455 kilohertz above that. So if there is, which is 15 to 10.
Right.
And if there's a signal there that's strong enough, it'll interfere. You'll get both signals. And if the local oscillator were below this, it would be at 13.8 something. And well, it'd be at 13.845. That would be the local oscillator frequency. That's the 13.45. And the image would be another 455 kilohertz below that. Follow me?
No, I'm sorry I asked, actually.
Too much information.
That's
Okay.
TMI. I'm just going to take the
That's
455 times 2 and add it to the 14,300 and answer the damn question.
There you go. That's it. You got it. What's
Thanks,
reciprocal
Chad. I was
mixing?
just kidding. I appreciate your explanation. I
understand.
I'm getting like, my brain is like mush right now. I'm just
Yeah, we're almost into information overload today. But we've got more questions we can go through. Let's do these real quick because we're getting close to running out of time. Reciprocal mixing is local oscillator phase noise mixing with adjacent strong signals. So you got to keep adjacent strong signals away from your mixer because that causes all kinds of problems. And this problem is the local oscillator phase noise. It's called reciprocal mixing. What problem can occur when using an automatic notch filter to remove interfering carriers while receiving CW? It can remove the CW signal also. That's for an automatic notch filter.
You skipped another question. You skipped what kind of digital signal processing audio filter is used to remove unwanted noise from an SSB signal?
Okay, I'll let you answer that one. What's the answer?
That's A, adaptive filter.
Okay, so DSP signals, DSP filters are adaptive filters that can take noise out of sideband audio. Let's see, I guess I'm a page behind. I'm sorry, that's why I missed that. Yes, I'm sorry, I left out another one. An adaptive filter is a DSP audio filter to take out unwanted noise from sideband. That's it. And this could also be an automatic notch filter taking out CW signal that you want. That's the problem that's using automatic notch filters. Okay, so we got the one we missed, right? You got that answered?
Yep.
Good, thank you. I'm glad you were watching because I kind of lost track of the page.
Somebody's going to keep you honest, Wayne.
Thank you. I'm glad you're listening. What's the noise figure of a receiver? Remember what that is?
Hold on. It's D, the dB noise generated by the receiver to the theoretical minimum noise.
That's right. That's the lowest. That tells you how much noise a receiver has inherently in its response. And it's not helped by noisy amplifiers. What is meant by the blocking dynamic range of the receiver? This is the blocking dynamic range is defined by the 1 dB gain compression point. The mathematics is the difference in dB between the noise floor and the level of incoming signal that causes that 1 dB of gain compression. But if you remember that blocking dynamic range has to do with the 1 dB gain compression, you get the concept and you get because gain compression is caused by large signals coming in. What's the purpose of a preselector in the receiver?
We had this one before, or something similar to it, is to increase the reduction of out-of-band noise, out-of-band signals.
Yes, that's right. And yes, some of these questions are repeated in the question pool. Sometimes you might get lucky and get them both on your test. Let's see, next page. We're on page 134. Yep, that's it. Okay. What does a third order intercept of 40 dBm mean with respect to a receiver performance? Third order intercept level of 40 dB. What does that mean? 40 dBm. That means when a pair of two 40 dBm input signals generates this third order intermod product that has the same output amplitude as either of the inputs. I don't buy the last half of that statement, but what the part that is correct is the third order intercept level of 40 dBm uses the 40 dBm input signals to generate this third order intermod product. The point is you've got two large input signals, two high level input signals that generates this third order intermod product. And that messes up the receiving of the channel that you want to be listening on. That's not it. Okay. That's all that question. Why are odd order intermod products of particular interest when compared to other products? Because the odd order products are likely to be within the band that you're listening to. And it would fall within your IF pass band. Odd order intermod products are likely to be within the band. How does a diode envelope detector function? It rectifies and filters the RF signal. If you just remember a diode rectifies, you've got the question right. But it's a diode envelope detector, rectifies and filters. The detector includes some kind of filtering of what is going on.
Yeah, and the simplest filter there is a diode followed by a capacitor, which short circuit the RF component to ground.
Yes.
And so you get the audio waveform off of the AM signal.
That's right. That's an envelope detector. Which type of detector
Sorry,
circuit?
can we go back a couple of questions? I had a question. What are they referring to when they're talking about third order intercepts? I mean, and the third order tones. What is that? Is that like the harmonics? Related to harmonics, or?
That's when these two high-level signals combine in the third order product, because you talk about the number of orders of products by the mathematics used to define a mixer. It's all in the mathematics of which power of input frequency multiplies by which power of the LO frequency. And this is a third order.
Yeah, frankly, I don't understand what they're talking about personally. This is one of those questions where just remember the answer.
Okay. Yeah, no, I was rereading what Gordon wrote here. I'm trying to digest it. I'm like, well, how are they? Where's the math being computed? Are they going off of harmonics on the inputs, or?
Well, he doesn't do a good job with the
Yeah.
mathematical explanation on this one,
Okay.
nor the measurement method. There's standard measurement methods, which is too much detail to get into. You certainly don't want to get into the mathematics of it, and Gordon doesn't either.
Okay. All right.
Okay.
All right. Thank you. Sorry. Yeah, I was just trying to read both of the answers on those questions. I'm like, what are they trying to digest here to us? So.
Yeah.
Well, I don't know any simple way to talk about third order intercepts without going into the math, and I don't know why somebody in the VEC group put a question like this in, but they got her in here.
Yeah, it's the weed question. Nobody's getting perfect.
Well, I have a problem with 40 dBm is a 1 watt signal. 30 dBm is 1 watt, and 40 is 10 watts. How in the world are you going to get a 10 watt signal, two 10 watt signals in a mixer?
No.
You know, and I can't wrap my head around it. So memorize the answer to this one, or just give them that one.
All right.
You know,
Yeah.
I would just give them that one.
Just put some notes on it. It's like, I don't agree with this math. All right. Thank you.
Right. Yeah. If you want to know the nuts and bolts of it, go Google third order intercept, and there's books written about the subject. So there's a lot to it. Let's see, we got past the diode detector. What kind of detector is used for demodulating single sideband? What type of detector would you use? That's the product detector. And we didn't talk about why it's called product detector, but that's not the question. It's the product detector. If you want to know, I can tell you, but it's not relative to answering the question.
Well, discriminator is FM, phase detector is phase modulation, phase comparator is related to phase modulation, single sideband is an amplitude modulation thing, and simplest product detector is a beat frequency oscillator with an envelope detector.
The envelope detector, same for CW.
But the mathematics is why it's called a product detector, because you're introducing a local oscillator frequency and you get the product of the two signals, one of which is audio, which you take away.
Oh, in the book, he does say beat frequency oscillator. That's what I learned in previous classes, but here he doesn't say that. He just uses product detector. Well,
they're more sophisticated product detectors than the beat frequency oscillator and a envelope detector.
Yeah, it's a lot simpler than that. Just do it in a DSP. Be done with it. The principal frequencies that appear at the output of a mixer circuit.